So hello again and welcome to part 2 of our structure analysis of a tapered wing. Now we finished our geometry here. Next we are going into the analysis part. So before that I'll just show you how you can use regular data or materials that are available in the ANSYS model, which is basically structural steel. I'm sure everybody would have seen that. I'll show you how to create a new material with the properties that you know. Okay, so here we are going to structural steel is already there. You can use that if you want. We won't make wings out of steel, so that's why. So what we'll do here is basically we'll create a carbon epoxy. Okay, so sorry, epoxy, yeah. So we'll create that, and I already collected all the values for the different properties of the material, so I'll show you how to input all of them. And when you are going to design your own wing for your own whatever material you're going to choose, you can just collect data for that material that is available online. Okay, so for carbon epoxy, so first thing is like density. Okay, so density, what I took is in gram per centimeter cube, so it's 1.6. Okay, I need a coefficient of thermal expansion, which is isotropic. That's in per Kelvin, so it's 2.3 into 10 power minus 5. Okay, and then I need Young's modulus, so those will be in this isotropic elasticity. So Young's modulus in megapascals, which is going to be 7,000 with a Poisson's ratio of 0.3, and it itself will calculate the bulk modulus and shear modulus, so we don't have to do that. And then I also have data on tensile yield, compressive yield, ultimate for both tensile and compressive. Okay, so all are in megapascals, so I'll give megapascal for everything, and the values 1500, 1000, 600 and 570. Okay, so these are the engineering data or the properties of my particular carbon epoxy material. Again, if you are going to choose a material and create it, you can find these values online itself. There are several tables for this. Okay, not only this, there are many other variables that you can take, but for our particular analysis, this is much more than enough. We don't even need thermal expansion and all, but this is enough. So here again, you can add new material here. Just click on here and then you can write it, type it down. Okay, so that's all with respect to engineering data. We can leave here. Now this geometry, we can take the geometry from here and then just basically do this. Okay, so we took the geometry from there. We'll just have to assign this new material that we have now. So I'll open mechanical. By the way, this is static structural, which I took from here. So let it open. You can see the busy symbol here. The red color one icon means it's busy. Yeah, many pop-ups will come. It's not required. Okay, so wait for some time. Let it come. Okay, so the process is over and we got our okay, stop doing that. Okay, fine. Yeah, we got our wing now. So this is our tapered wing, which we had designed earlier. As you can see, it's pretty shiny also. Okay, anyway, that's not important. See, this was a surface body that we unknowingly brought in. We don't require that, so it's okay even if it is question. If there are question marks here, it means something information is incomplete. See, it doesn't have a thickness. What is it is asking? It's not required here, so it doesn't matter. Like, you can just leave it. What we are interested in is a solid here. Okay, so this is what we are interested in, and for this we are going to assign our new material, which is carbon epoxy. Okay, just change that for the solid alone. It's green color text, so it doesn't matter. These things you can leave it as it is, or we can suppress it later if you want. Okay, for now I'll just leave it like this and then finish the setup here. Okay, so we have finished that. Next we need to mesh this. Okay, so here I'm not going to do any kind of meshing tutorial here. We'll just mesh it generally. because if you're going in depth of how to mesh this, it will take a long time. Okay, so for now I'll just hit generate mesh, and it created a, okay, it looks kind of very bad. One second, let me just clear that and hit generate mesh here. Okay, it's the same thing. Okay, so what I understand is it's probably because of the surface body data here. So let's just suppress those and then try generate mesh again. Yeah, we got a better one now. Okay, even though it's not a very last time it was very rugged, right? That's because the solid body got meshed separately and these two surface bodies got meshed separately. Okay, we don't need that, we only need the solid body. Okay, it's not yet the best mesh that we have, but it's okayish. Okay, it's maybe we can go for 100 element size and then try it again. Okay, let's see what happens. Okay, it's much better, but not the best. Let's just reduce it again and see. Again, this, since this is a 3D mesh, I won't ask you to go do a very very good mesh on it. It doesn't necessarily have to be for your experiments, but if you are doing for a company or something, it has to be meshed very accurately. That is why people usually use some other software like basically hyper mesh or something for meshing it exactly to the point and whatever scaling factor you need it to be. Sorry, not scaling factor, aspect ratio you need it to be. So okay, yeah, now it's much better. I think element size of 10 did the trick. Okay, so we have our it's very beautifully meshed as well. Okay, now one thing you need to realize is this is not surface meshed. Okay, the inside is also meshed. You can't just you just can't see that all of them. Okay, so the insides are also meshed. And what I mean about using other softwares like hypermesh na edhukku sonna appadina, see, from the general mesh that we did here, all are square boxes, but look at here, we have a triangular element here. This is not what we need. Okay, we don't need these kind of things, or these will create you can't call this a very good mesh. That's why. Okay, we need it to be just square boxes all throughout. So those kind of things can be done if you are using hypermesh. See, you can see a triangular. This is not a triangular; it's a quad, but still, look at the shape. It's very uneven. See, take a look at here. It became like this. You won't get enough proper data points here. So since this is a structural analysis, it doesn't really matter. But if you are going for a fluid analysis, yes, of course, it will very much matter. Okay, how your mesh is going to be. So anyway, this is more than enough for us, I believe. Let me just save this quickly. I don't want to lose any data. Now we can go ahead with setting this up. So this is a wing. So basically it's a cantilever, right? So what we will do is our usual thing. What we did for a cantilever, or we fix faces, right? So go here, hit fix support, face is selected, click on this face. Okay, and then apply. So that is your fixed support. Next, what we will do is we are going to assume this wing is going to be in a kind of flight. Okay, so during flight condition, what is going to be it's we'll structurally analyze it that time. So for that, what load I'm going to give is rotational velocity for the whole wing. Okay, yeah, for the whole wing, defined by components, and I'm going to say that along the y component, okay, it's going to be 105.62 Okay, radians per second. I need it to be 1 second. Let me just check what my units were. Okay, I need it to be in RPM. That's why. 1 second. Yeah, I don't need 1000 RPM. It's just 5.62 RPM. Okay, so this is the force that we're going to apply on this. It's just an assumption. Okay, we're like trying to say that the wing is in motion. Okay, and in the solution part, we need things like total deformation, and what else can we take? Maybe equivalent stress and equivalent strain. We can, if you had inserted other data, we can also use the fatigue tool to find the fatigue also. Okay, that is also possible. But we don't have anything here, so we'll just leave it like that. And yeah, okay, so this is like an assumption where you are having the wing to be flying. Okay, that's why he gave this rotational velocity here. And then we'll hit yeah, that's all right. So we'll hit solve. So again, this solving time will depend on your system processing part. So if it's not up to the mark, it will take some time for it to process. So also, like, depending on the mesh, since I gave a very good fine mesh here, it will take some time for it to analyze as well. Okay, typically, like if you remember in the previous problems that we did, it took only 2 or 3 seconds, right? So it's taking some time here, some 20-30 seconds it's taking. We'll wait for the thing to finish. Okay, I'll just resume it when it finishes. Okay, so that took around a minute and 30 or 40 seconds. So yeah, you can see in the solution how much memory of my system it used, and the resulting file is almost 220 MB. Yeah, it took 2 minutes. Okay, so yeah, so we found our results here. Okay, so this is the total deformation. We can no wireframe, yeah, and then contours, smooth contours. Okay, so this is our total deformation. Okay, so it has deformed pretty much. The maximum deformation is in the end, as you can expect of a cantilever beam. And you can see the equivalent stress here. Okay, and you can see the strain also here. And the values are different, but the color remains the same, as you can see here. Okay, so like last time also, we can do the animation here as well. So it will take some time because my mesh count is very high, and even my analysis took some time. So I'm not sure whether it will work. Let's see. Okay, that's a very beautiful animation that we get. Okay, you can see how it, right? So when it is flying, this kind of deformation happens. That is what we are seeing. Okay, so in reality, it's not going to be so much of difference. It's just 1.4 mm. What they're showing here is like almost 10 or 15 centimeters or something. So this is just for us to have a look through how this is going to be. Okay, now this is one way to analyze when you are talking about a aircraft in flight. Let's say you're not going to do that. You want to find out what is going to be the details of structural analysis of a particular wing when it is in on the ground, okay, when it is not flying at all. So in that case we can we don't need this rotation velocity. Fixed support will be there, it's a cantilever. What we will include is, we will insert, let me see if I can find it, yeah, standard earth gravity. Now this is a cantilever beam, yes, but at the same time, if it's going to be a wing from an aeroplane, it has to be in some particular direction. So here I believe it's a negative y, right? Yeah, so in the negative y direction we have Earth's gravity value. It itself took 9.8. So we can give this, and then the same solution set we can give. You can give other data also if you want to calculate those, and then hit solve. Your stationary wing structural analysis will be done. Okay, so again I'll just pause here and then resume when I get the results back. And yes, we have the results now. As you can see, this took even more longer. It took 3 minutes, almost 4 minutes. And yes, we got the results here. Okay, here you can see even the stresses. Since this is stationary, you can see how the stress is more at the fixed end of the cantilever beam or the wing. Okay, it looks even bent a little, right? Let's try to animate it. See, even the deformation value is higher here. Okay, so this is a total deformation. Okay, just keep that in mind. It involves all the in all three axes. What is the deformation is given here. Okay, so this is just because of gravity, your wing will drop down. Okay, so yeah, this is with respect to your structural analysis of a tapered wing. Now you can change all these settings, try different variations, change the material. Now if you think about it, we gave some properties of a material called carbon epoxy, and it just assumed the entire wing body to be carbon epoxy. Okay, even the interior of the wing is carbon epoxy, but in real life that is not possible, right? You won't have, you can have it for maybe some kind of model plane, but general over plane editing inside your wing it will be ribs, and there will be fuel tank and all those things will be there. Okay, so if you are going to do an actual analysis, you'll have to include all those inside your design. But for our case, to understand how this is done, this is much more than enough. Okay, if you want to take this a further step deeper, you will have to design all those intricate things inside the wing, assign materials for every one of those, and then you can do the same analysis again. The process is the same. Okay, just designing all those individual components and assigning materials to them. That's the only difference. This analysis process is the same. Okay, so with that, this session is over. I'll see you again in the next class.